Hello everyone, my name is Jakub. I'm really glad to be here. And today I'll be talking about Catstagless and the cool things you can do with it. Uh, let's do it. So first I'm going to give you a teaser, like an introduction to one of the reasons why you might want to use Catstagless. So let's just do it. So let's imagine we are writing code in tagless final. I don't know about you, I do this kind of every day. So you have these sort of algebras or interfaces parameterized with an effect type, and you have dependencies on other algebras or such interfaces, and you have these kind of factory methods. Maybe you are you have a class and you're accepting constructor parameters. Doesn't matter, but you have these dependencies, and ideally you would like them to be in the same effect, and you would also like to be like your algebra would also be in the same effect. So you'll have just one f, everything works in the same effect in IO or ZO or whatever you are using. And this is like the perfect scenario. Like if you're doing this kind of this style of programming, this is what you want to have. But sometimes life is not that easy, and we have to deal with other effects. For example, because of transactionality. So if you are working with Doobie, a database library, then you have this connection IO type, which is also an effect. It's also a monad and so on. And when you convert that using a transactor to some other effect, then the transaction is committed on this like block that you are transacting. So in this piece of code, uh, when we do order repository save and transact, then this is the transaction boundary. The sending of the message is like not part of the transaction. And sometimes you want to do this, sometimes you want to wrap the whole thing in a transaction. But still, if you are like mixing these concerns, then your code has to deal with multiple effects. So basically, yeah, you now have TF, you have the connection IO, you have a transactor, and you need to transact. So a bunch of stuff that you wouldn't really like to care about in this context. You would like to just write your business logic with one effect, just call the methods, compose them like on the previous slide, and that would be it. So what would we need to have something like this? Well, first of all, when we call this method, when we construct our order service instance, we would need all the dependencies to be in the same effect. But we wrote our repository in the effect of connection IO because that's just what Doobie gives us. And the sender is written in IO, for example, because the constraints on the effect in it are very high. Like you need concurrent effect and all that cats effect stuff. A lot of power, and you just cannot get that for connection IO. So you need to go with IO, and then only then you would convert back to connection IO. And this is possible. We can implement this for sender, for a simple interface. Well, pretty much any interface parameterized with a type constructor like f that returns methods in f. We can do this. We can wrap it by basically creating a new instance that just calls the underlying method and then converts it to the other effect. We can do this like this too method works because you can convert IO to any async type from cats effect. And as it turns out, connection IO has an instance of it. So this works. You could just, yeah, you could do this for any other effect with that instance. But this is a very specific. First of all, this is very concrete about sender. And second of all, it's very concrete about IO and connection IO. We cannot really add that much abstraction here. Like we could very easily hide connection IO and replace it with something else, but then we still have IO and sender. That's probably the most important thing. So let's try to add some abstraction to it so that we don't repeat ourselves. And one thing we can do is uh, basically hide the IO and the connection IO. So we replace them with type parameters that are also type constructors in the change effect method. And we accept a function from f to g, except this doesn't work. It doesn't work because f and g are not of the wrong kinds. And what I mean by that is that when you have a normal function, like a function 1 or the fat arrow type, you have fully like concrete types. They have values. These types like A and B need to be types that have values, or maybe not if you have nothing. But in theory, you could have a value of this type, like list of string or integer or option of Boolean, something like this, not list or IO or option. So we have a function, if we have a function, we can provide an A and get a B instead. But what we really need in this case, that why we cannot run this, is that we need something more. We need a function that for any A will go from an f of A to a g of A. And the really important part is that the A is the same on both sides. It's just that the type constructor changes. So the effect changes. And we need this as a value because we are passing it as a parameter. So we cannot just have like something of the shape of apply here, something that is parameterized with A. We need this as a value. So we, well, basically folks in Scala created function K. And this is available in cats. So we have just one small change to make this compile and work. We need to replace the fat arrow with the squiggly arrow, and now it'll work, it'll compile. But still, we haven't solved the other problem. We are still very specific about what sender is. So let's change that. Let's try to abstract that away as well. So now we removed sender from the signature and we replaced it with a higher-kinded type alg that will represent some sort of algebra. And we will be going from an alg of f to an alg of g using a squiggly arrow from f to g. But we are not able to do that. Like we know nothing about the structure of alg, and we are not able to call any method on it. And what is more, we know nothing about how to create an instance of it. So are we doomed? Is this where we have to stop abstracting? Well, I don't think so. And as it turns out, this should be pretty familiar to many of you, because we are using a function from one type to the other type and lifting it to a function between some other things with these types. So from a squiggly arrow from f to g, we are going to a function from alg of f to alg of g. And we have a similar pattern somewhere else in functional programming, in which we go from a function from a to b to a function from f of a to f of b. And that's a functor. That's mapping on a functor. It's pretty much the same. And in our case, we will need something more than a functor. We will need a higher-kinded functor, let's say. And in Catstagless, this is called a functor k. And it allows us to map k on an algebra, just like you would on a functor, except you need a squiggly arrow, a function k, and not just a normal function. So the shape of functor was pretty much like this. We lift a function to a function between effects. And now we lift a squiggly arrow to a function between algebras. So with Catstagless, we can derive this instance of functor k for any algebra of this shape. Like you have a type parameter f and a bunch of methods that return f of something. It doesn't have to be one method, it can be any number of them. And if we have an instance, if we have a function from this one effect to the other effect, we can map k with that and then call methods on the result, and they will be in this new effect. And this is much more powerful than it might seem from this slide. So now that we know about the things that we can use from Catstagless, at least one thing, the functor k abstraction, let's see what cool things we can do with it and other abstractions in that library. I already mentioned we can change effects. So we can apply a transaction. We can go from a transactional type to a non-transactional type. That's what I already showed you. But we can go with this idea. We can push it much more. And we can go from types like writer t to IO. Maybe you want to take whatever was written in this writer t value, send it using a function, or like a sender, whatever, and then just return the underlying effect, so the IO. And this will also work on, and we can abstract this to any kind of algebra that has a functor k instance. I'm just being explicit here to avoid noise in the code. And we are using a special syntax from Kind projector here in 2 places. The first one is in writer T of IO messages in star. This basically means that the star is where the type will change. Like this is where the A will be, but everything else will be, the F, the writer T IO and messages. We can replace that with, for example, just IO. And the other place where we use the syntax from that library, it's actually a plugin, compiler plugin, is creating a function k instance, the send value. So this is just an easier way of saying new function k from this to that, def apply, and so on. All right. We can do other things. Instead of just changing types, we can stay in the same type, but add some like callbacks, if you will. We can do things before our call, before the original call to the implementation of the function, and after the call. There's just one problem with this, like in the general case, we know nothing about the return type of the call or the parameters. We don't have that information because a function k is like universally quantified. It needs to work for every a, not every a that has a show instance, just every a. And we are not able to work around that, not with the current shape of functor k. But maybe there's a way, which I will talk about later. So here we are just using the two-string of the result. It will sometimes work, but that's just a toy example anyway. But we can do this. We can do this, and it'll compile and work. Another thing we can do is catch errors. So we can go from, for example, IO to either T of IO, but this IO will not fail. We could use a different type like UIO if we had one in cats. That would be unexceptional IO, so one that cannot fail with a throwable. But we are able to just change the effect in a way that will move the errors from the IO to the either T channel of errors. That's just one more thing that we can do with functor k. Now, functor k is not the only abstraction that's included in Catstagless. We also have apply k. So this is basically a higher-kinded variant of apply. What it allows us to do is take 2 algebras, 2 implementations of the same algebra, potentially in different effects, and do something with the implementations of each method, like in this algebra and this algebra. So in this instance and that instance. So we have access to the implementations of both of them, and we can combine them in some way. But we still only know that they are IO of something in this case, because they are both in IO. But we don't know anything about the types. So we can only use methods that are like very generic. Here we are using or else to fall back from the first implementation to the other one, because that's exactly the type of or else. We go from IO of A and another IO of A to an IO of A. And this works. So that's another thing you can do. Fall back from one implementation. If it fails in any method, call the same method in the other implementation. Or we can use the same idea, but use concurrent of IO to run the 2 IOs concurrently, 2 implementations of the same method. And if one completes first, cancel the other one and keep the result. If they both complete at the same time, just choose one. But this is quite powerful as well. You can use this to run like maybe health checks, choose the fastest health check, or maybe you want to retrieve tokens from some storage. And if one action, for example, takes too long, like a couple seconds, then start another one. And maybe you want to like do this completely separately from the implementation of user service. So this would be something you might use for that. Or we can do something as simple as lifting a stateless instance. We can implement user service in the ID monad, which is just ID of A equals A. It's just a clever compiler hack that allows us to deal with no effects as an effect. So we create a user service in the ID effect, and then we can create a polymorphic value, polymorphic function value, which is function k, from this a to IO of a for any a. Then we can use IO pure. There's really nothing else that fits this shape, and well, nothing else that fits this shape without any extra effects. And we can map k our instance, just change the effect. That works as well. And we can push the idea of apply k, the one that allowed us to combine two algebras, two values of the same algebra. We can push it forward and have more than two. We can have like 3 or 10. We can derive methods on the companion object that will use the apply k and the functor k instance to combine more than two. So in this case, we are combining like 3 implementations of the same algebra. Except here we have a problem that when we combine them, we will get a tuple of all the calls. We could get a tuple of all the results, but we cannot do anything about these results. We know they are of the same type because it's the same method underneath. But we don't know which method, and we don't know what the type of it is. So we cannot combine them with like a semigroup or anything like that, unless we explicitly call one concrete method, like find all in this example. But that's just a limitation of the current shape and not something that we couldn't work out. Or we could even, like, this is something that I came up with, like, probably it's not very useful on an everyday basis, but maybe someone has a use case like that. We could lift an instance of like an algebra in IO to a streaming one, which will just repeat the calls to this action in a like exponentially growing manner. So like run this once, wait 100 milliseconds, wait 200 milliseconds, wait a second, whatever, and we will keep all the results as a stream. Like I can see how this would be useful. Maybe it's not, but it's still quite cool that we can actually do this. Or things like adding a semaphore, a circuit breaker, some sort of rate limiter to all the methods. We can do that as well. We can add retries, any kind of retries. If you are using Zio or cats retry, you could attach a retry policy to an IO in every method in the whole algebra, no matter how many methods it has. So it is quite useful for eliminating boilerplate if you are doing this kind of thing. Now there's a very powerful thing that's quite new in Catstagless. It's called instrument. So it's a typecast that allows you to attach information to each method. You will get the name of the method and the name of the entire algebra, which could probably just be a, well, it's not that much of an effort to get the algebra name, but then you have this, you can abstract on this and create methods that operate on any algebra that has this instance. So what it allows us to do is, for example, when calling any method in the algebra, we can log its name, the name of the method and the algebra. Like this may not be like super useful, but it's nice that we can do this again. Or you might want to disable certain methods in an algebra, and like methods which have a specific name or whose name is matches some sort of pattern, and you would replace them with like failing implementations. Or you might want to introduce delays to some of the methods, like not all of them, but just some. You would probably use instrument for that. And this is probably the most useful one. You might want to create a span in a distributed trace, which has the name of the method in the algebra. That would be quite cool. This is using the Natchez library, which is very cool for tracing. I recommend you check it out. And this is also quite cool. We can map K on multiple algebras at once. Like if you create a trait that contains members that are all algebras and have functor K instances, you can map K on the entire thing, and all of these algebras will be replaced. So you can add, for example, a new span to a trace in every one of these algebras methods. And I think that's also very cool. If you are using this kind of pattern for building your services, that you are having like all of them in a single module, then this might work very well for you. So is that it? Well, there's quite a lot more we could do in theory in the future about using abstractions like what we saw in Catstagless. For example, if we had access to parameter values and names, we could generate the keys for caching as a single method. We could add a cache to an entire algebra with a single method call using an instance of using the metadata about the algebra that was generated only once for the whole compilation in the instrument instance or something similar. Or about tracing again, you might want to add the parameters or certain parameters as tags in a span. That would be also very useful to look at. And if any method in the algebra fails, you might want to log the parameters or maybe some parameters that it had, like maybe parameters starting with an E or something like that. Or something that I talked about before when we were combining 3 implementations of the same algebra, maybe you might want to combine them into one, like using a summary group. So for logging parameters, you would not only need, or for passing them as tags, you would not only need just the names of them and access to the value, but maybe some typeclasses for them, like maybe a show instance. That would be very, very nice to have. Now, can we do it? Not at the moment. We don't have a tool for that in Catstagless, but there's an ongoing discussion that you can join, and I recommend you do if you're into this kind of thing. All right, so we have some time left. So I'm going to show you a demo because I actually worked on this a couple days ago. So can you see the code? Someone nod? Okay, there's some nodding. Cool. So I'm actually going to write it down right now. Let's try to do some live coding. So the shape of this thing that you would use would be something like with return type. We will add return types to the, so we will not add return types, we will add typeclasses for the return types. Let's do a quick demo on how we might log the return value of each method in an algebra, but using the show instance. So let's say like return, that could be a good name. So this would have a single method that would convert an algebra of an effect f to an algebra with some constraints on each method or the return type of each method. So what this will look like, we'll have an alg of f, but we will return an alg of constraints. So this is quite surprising. At least it was to me, but let's see what we can do with that. Right, so let's try to implement this for like a sender. I'll have a sender that will result in an f of int. Like, I don't know why it's an int, let's just pretend it's a real thing. And it's going to have a functor k because I'm going to need it. And also, sorry, it's not a functor k. And also I'm going to need an apply k, so I'll get that. Right, and let's try to implement an instance. So I don't have automatic derivation in using the compiler or macros for this. So I'll have to write it by hand, but ideally you would have something more automated for this. Let's hope we can do this in a couple of minutes. Okay, so that'll be return type of sender. And yeah, I need to implement this one method. So I'll create a new sender. And now I'm pretty much doomed. Like, I cannot implement this. I have no idea how to get constraints of int. I don't know what it's going to be, what the constraint is going to be. It's going to be a monoid, it's going to be a show. So I'll need to customize the original method. Yeah. So I'll actually need instances for each of the return types in the algebra, but I don't know about the types. So let's call it like types. I'm just making it up. And that's going to be an edge list. I'm going to use shapers just to not invent things again. And I'm going to need all the instances. So that's going to be lift all from, we're going to lift constraints, and we are going to lift types of class ID. So basically, we are going to lift an edge list like int hcons hnil to the typeless instances. We'll have types of constraints. Just trust me, it's going to work. So is that it? Oh yeah, I need the aux pattern. And that should work. So I need to be more specific about the types here. This is going to be C of int and hnil. Import hnil. Okay, and then I need to repeat that here. And I need to add this. So I just copy it from the parent. And yeah, I think I can get the instance now. Select. Okay, so I got it. And now I can try to implement this logging thing. We're going to need a console and a monad of the effect, and I'm going to take a sender of the effect. And that's probably it. So I create a new sender, and I'm going to basically map to K this sender with the return type implementation of it. So I'll import the syntax for return type. It's the wrong one. 1 minute, I think. This is going to be a function K from tuple to K of f show and, oh yeah. No, this is not going to work now. All right, I just showed the whole thing, which I have somewhere here. Log result. So basically what we can do is just, we can zip the original implementation with the one that instead of effects has instances of the return types. And then we can use that like a show instance of this return type to display it after getting the value. And this will actually work. So you can check out the code later. I'll just finish now to not run over time. Where's the slide now? Okay, so this is all I have. Thank you very much. I hope I wasn't over time.
Thank you, Jakub. Yes.
Yeah. I would like
Thank
to
you
just
very much
ask
for
you
your
to,
talk. Yeah.
sorry?
No, go on, please.
Yeah, so just follow me on Twitter, read my blog, and find me on YouTube.
I don't have enough experience with cats to really say something intelligent. You know, I'm kind of in learning mode about cats as well. I guess it seems to me that, you know, for people who used to use Scala Z, now they're using cats. Is that correct?
Well, I guess many people will have that situation. Like I actually used Scala Z first, but only for like a couple of months in a single project. And probably the biggest reason why we went with Scala Z for the time being was just that cats wasn't stable yet. So that was just a couple of months before cats went 1.0. But all the concepts that we used translated directly to cats. So It was some knowledge that wasn't lost or time wasted.
So is everything in Scala Z in cats?
No, I don't think so. There's some of the more advanced, like hardcore things, like probably things like the store common add. I'm not sure it is in cats, and there's plenty of other things that are missing. So Scala Z had its own future type, its task type. There was probably an IO as well. I don't remember right now, but well, cats was from the beginning probably more focused on being modular. So that's why the cats IO type is in a different library now, and it was actually quite a lot of time before it was released after cats itself. So yeah, it's not like a one-to-one rewrite, or not even all the things are in there. But cats also has some things that were not in Scala Z. I think the parallel type class was not, well, there was nothing like that before, I think. But I wouldn't, I'm not like completely sure. It's just.
Does cats let you get done everything that you need to get done?
Well, no, I don't think any library will ever do that for you. But when it comes
the cats
to
like things.
Yeah, okay, I understand the question. I don't think it ever gets in the way of me wanting to do something. So maybe even if it doesn't allow me to do something like out of the box, it doesn't prohibit me from doing that. Unless I want to do something on sound, like treat any type as I don't know, as a particular type, like cheating the compiler basically in situations when you don't have information about the type. You might want to pretend it's something more specific, and then I guess no library will ever solve that problem. But yeah, it's not a pain to work with. Well, it obviously depends on what you're doing. If you're doing a lot of Spark, then probably it might be painful to use cats with it.
Thank you.
Thanks.
I have a question, Jakub. Could you compare somehow cats and Zio? So what the spheres, when one implies better comparing to other?
Mm-hmm. So, of course, it's not a black or white situation.
Yeah.
So depending on what you are looking for, you will find more value in one or the other. Of course, there are also some not so major differences in the behavior, which are usually on the side of, well, Zio being better. That's just because by the time Cat's effect stabilized, so which was in 2018, some of the downsides of the existing abstractions were not that well known. Well, we didn't really realize the limitations that gives us. So because they stabilized the Cat effect library, at that point there was not much more they could use to solve some of the issues that Zio discovered later, and change the APIs, the design basically of the whole library to solve the problems. And I'm talking about like things related to shifting threads, like when you're going onto a blocking pool, doing that transparently to the user so that you don't have to carry around information about how to actually do blocking, or maybe shifting between async, async operations and getting back to the same execution context that you want to run, and this kind of things, and also some interruption. So I think a lot of the advantages that Zio has are because of the ability to sort of improvise and to improve the to make breaking changes because still don't have a stable API. But that's just one difference. The approach to well, it's not one difference. There's quite a few differences that are caused by that like cats, at least in the API, didn't change that much in the last 2 years, but Zio did. So that's one difference. And there's also the fact that Zio is trying to appeal more to the non-functional side of Scala developers. So it's not trying to create abstractions for doing FP with different effect types. It's trying to provide a tool set of easy to use parts that connect well to each other and allow you to get a lot of power with not too much work. So when you come from the world of futures, you will see a massive improvement if you want to do concurrency or basically advanced effect-based code. But in cats, there's probably a bigger learning curve as well, because not only you have to learn how to do pure concurrency, you also have to, well, it doesn't offer such a rich API directly, at least the IO data type. So if you want to get something more advanced, you have to basically use some of the type classes that we know from cats, or the new ones from cats effect. So for the more powerful things, there's a bigger, maybe not even just a learning curve, but it's harder to get there. Even if you know what you need to still like combine several things. And in Zio, you have many of these things like out of the box. So in that matter, it makes it, Zio is more similar to Monix than to Cats effect, because it offers a single data type, well, a single core data type, the task or Zio type, and powerful operations on top of that, instead of a small type and a lot of abstractions around it. I guess that's the biggest difference. And also the approach to having dependencies. So in Zio, it's pretty much recommended to use the environment type to have dependencies in your programs, whereas cats.io doesn't really play well with that, and it's more you're encouraged to pass dependencies as constructor parameters or function parameters. If you want to be abstracting the effect, you do like tagless final and higher-kinded types approach, which is significantly more complex and harder to learn for beginners, but well, depending on how your project looks like, it might give better returns in the future. So it's a game of trade-offs, basically. Choose your own effect, yeah, depending on what you're looking for. So this is actually why I think everyone should try out different approaches if they have to choose, because depending on the use case, the answer might be different.
Okay, thank you so much. We are usually asking about your regular technical stack that they're using. So what libraries, so besides cats, they are using? Maybe some tooling that you prefer. Could you share?
Okay, so in my team, we have mostly standardized on a mixed stack. So we use, for example, for databases, for talking to Postgres, we use Doobie with Quill. So it's a quite well working combination. You get the the completely functional approach to running JDBC programs with Doobie, and you get a nice DSL on top of it, thanks to Quill. So that works quite well. For the HTTP part, we use Akka HTTP, but it doesn't really matter that much in the ergonomics of using it, because we are not doing a lot of Akka HTTP based code directly. We are using an abstraction layer, which is Tapir. So if anyone is not familiar with it, it's a library that allows you to define your endpoints, your HTTP endpoints, as data, which can then be converted to a client and the server using the same object. You can derive basically and implement a route, like an Akka HTTP route or HTTP4S route, and also a client like using STTP or whatnot. So we are doing exactly that, and it's working quite well if you are willing to have a lot of basically have the binary dependencies between your applications, because one application that exposes certain endpoints will expose a library with the client based on these endpoints, these routes, and then the other application has to pull that in. So whenever you have to make a change sometimes it takes quite a few library updates to propagate the change from one place to another, and that's not working well if you are sharing that between teams, because the more diverse the tech stack will be, the more these dependencies will hurt. So we are using that only in communication between services of a single team. And between teams, we are starting to get into contract-based testing. And for that, we are using Scalapact, and we're also making our own library that solves problems that we didn't solve with the other libraries. We eventually hope to open source it. And for normal things, our effect type is eventually IO, but most of the time, actually, yeah, all the services that we are writing, all the business logic, as an effect, it uses an abstract effect, an F, which is then on top, like in the main module of the application. It is defined as mostly writer T of connection IO, which is the transactional type from Doobie. And in that writer T, we have a log of messages to send, which is like a chain of message. And yeah, that's it. And then this writer T of connection IO is converted to a future for Akka, and that's basically it. And that's in one place. The whole conversion is just in one place, and you have a single transaction per request. And after the transaction is committed, the messages are sent. And that works quite well.
Great. Thank you for such detailed answer to the question.
Yeah, so it's been a great pleasure as always to speak here, and I cannot express in words how friendful the Ukrainian Scala community has been to me and to everyone else that I've seen. So it's a great thing you're doing, and I hope you keep doing it. Yeah. Maybe in the future, the conference, if there is a future, if we survive, if there's when there's another ScalaUA, maybe it can be more oriented towards the like multiple styles, like
yes,
being local and also being remote,
yeah,
so that people from the whole world can join in.
Yes, that is something that we are having in our mind, right? Yeah, yeah. Thanks for having me, and I hope to have more opportunities to speak at ScalaUA and meet you all. Bye. Bye, bye, bye.